Welcome class, and today's video we're going to be talking about covalent bonding. Now this CO is very important here because it refers to the fact that the electrons are actually shared in this type of bonding. So if you like, this little electron coin here is shared between bonding parties. Now if we go back to our previous type of bonding, another classic type of bonding, is called ionic bonding. Now in ionic bonding, there's bonding between the metal side of the group, which will usually, the metals will tend to give away electrons and become positive. And then over on the far side of our periodic table, there are the non-metals, and they will tend to become negative. So let's have a look at that type of bonding here. A good example would be lithium and fluorine. Now when we look at the outer shells of lithium and fluorine, we see that lithium has one electron, and if it can get rid of this electron and drop it over onto the outer shell of fluorine, then these would both have a charge. Lithium would have a positive charge, fluorine would have a negative charge. And so what we end up with here is LiF, or lithium fluoride. So this is in the case of metals bonding to metals. But what happens in the case of non-metals over on the right side of the periodic table, bonding to non-metals? Can that happen? Will it happen? And what kind of bonding is that? Well, it's a different type of bonding. It's not ionic bonding in this instance. And because these two fluorine atoms both need an electron to fill the outer shell, in other words, they don't want to give electrons away, a compromise, if you like, is to share the electrons. So fluorine is a diatomic molecule, which means that it bonds, it is found in nature as a pair. And the reason for that is because fluorine can bond to another fluorine, and the actual electrons are shared. So the electrons which are shared are right in here. And so we can represent this dot and cross, and these are the shared electrons, with a line. And that basically means that one electron is shared from each fluorine. And then we can count the electrons in total on the outside. 1, 2, there's 2 in here, and then so that's 4, 5, 6, 7, 8. And it would be the same on the other side of the fluorine. And so this fluorine, this F2, is an example of a covalent molecule. Also, it can happen with different elements. So an example here would be hydrogen bonding to chlorine. And we can recognize that, hopefully you can see that hydrogen just needs one more electron to have a full outer shell. Chlorine also needs one. And so what we have in that situation is hydrogen bonded to chlorine and bonded through this bond. And if you like, on either end of the bond there is an electron shared. And so that's a good example of covalent bonding also. A second important thing to note here is that the covalent bonding is not always a single bond. Now it was in the case of fluorine, but in some cases there can be a double or triple bond. And how would we see that? Well, fluorine has 7 electrons in the outer shell. It needs 1. Oxygen has 6. It needs 2 electrons to fill the shell, and therefore it will have 2 bonds. Nitrogen needs 3 electrons, 1, 2, 3, and these will be in electron pairs to have a full outer shell. So it will have 3 bonds, and carbon needs 4 electrons, and so it will form 4 bonds. And so the number of electrons needed is equal to the number of bonds formed. And so if we look at an example of that, a very typical example would be, let's look at 2 oxygens bonding together. And if we can draw what's called a Lewis diagram here, which looks at just the electrons on the outside, we would see that oxygen has 6 valence electrons. So each oxygen is going to bring 6 valence electrons to the party. And that means that each oxygen is going to require a bond forming between these ones here. And so if you like, each oxygen donates or shares 2 electrons, and that means that each oxygen now has 8. And so when we draw this, we will see that sometimes it's drawn as a double bond here, and that's because each oxygen actually donated 1 and 2. So it has 1, 2, 3, 4, 5, 6, 7, 8. So the number of electrons needed tells you something about the number of bonds formed. And so from this, for example, we can see that carbon will form 4 bonds. So it tends to form a lot of molecules and form high chain molecules. So let's just look at this in practice with 2 of the legends of our molecular world. 2 molecules which are used in our world lots. One of them which is used in the energy industry hugely at the moment, methane. And one which may be used in the future, which is called ammonia, which would not have the carbon dioxide problems for our planet that methane would have. So methane is CH4. Let's break it down how we get to that. One of the ways that we can do it is to use what's called a Lewis diagram. Again, just putting dots in for those valence electrons. Carbon has 4 valence electrons. And we start with the atom which has the most bonds. And carbon is likely to form 4 because it has 4 of those single electrons. And each hydrogen is going to bring 1 electron, 1 valence electron to the party. Okay, so we would see something like this. Again, what we're seeing here now is this shared electron pair. Okay, and what this means is that carbon now has 2, 4, 6, 8. And each one of those hydrogens now has 2 electrons. So they both have that stable outer shell, which brings more energy stability. And when we're recognizing how to draw this, we would draw it as such. We would have the carbon, and each one of those paired electrons we can simply write as a line. So this is a good example of a very simple covalent molecule, methane, which is carbon bonded to 4 hydrogens. And what about the new champion to the throne, ammonia? Well, let's draw our ammonia. We start with our nitrogen. It has 3 bonding capacity, so we're going to put it in the middle, and we're going to put in the valence electrons. And now we'll see that there is 3 singular electrons, 1, 2, 3. That tells us it's going to bond to 3 different things, and hydrogen will be more than happy to set itself to bond in this case. And what we've got here is we've got our 1, 2, 3. And so we can simply draw ammonia as this one here. Later on in chemistry, you'll find out that these 2 dots up here actually do mean something. They're very relevant in terms of the shape of the molecule. Now, we did start this video by saying that sharing is caring, but is that sharing only caring if it's done equally? Is it equal sharing is caring? I don't know. But in the covalent molecule world, sometimes the sharing is equal, sometimes it's not. So an example of equal sharing here would be this chlorine bonded to another chlorine. Both of these chlorine atoms just need 1 electron to have a completed full shell, outer shell. And remember, on this diagrams, we're just showing the outside shell of the Bohr Rutherford here. But you can see that in this case, there is a bond between 2. Both chlorines are going to want the electron the same amount, if you like, if they could want things. But that's not always the case. Now, when the electrons are shared equally, that is something called non-polar. And because there's an equal sharing of electrons, it means that one of them doesn't become slightly positive or negative for any length of time. So it's a good equal sharing of this electron in the middle. Now, what about an example where that doesn't happen? So if we look at hydrogen over here, hydrogen we said is just going to have 1 here. And the hydrogen is going to come in and bond here. Now, the thing is, when that bonding occurs, the chlorine is more electron hungry than the hydrogen. And there's a measure for that electron hungriness, or hunger if you like, and that's called electronegativity. And that's a value that shows how a element is going to do in terms of how much it wants electrons. Electronegativity, it's a big word. So this one is going to show the electronegativity values that when you look at both of them, there's going to be a disparity, a difference between them. And what that basically means is the chlorine here is going to hog the electron. And so the electron's going to spend a bit of time over here and then mainly over here and then back to the hydrogen and a bit more time here and then back to the hydrogen and then a bit more time here. So it's an unequal sharing. And what that means is because the electron is unequally shared, it means that this chlorine develops a little bit of a partial charge. Just show like this. And the hydrogen develops a partial plus. And because of that, we say that they're almost charged, and that's called polar covalent. And that's something you learn about later on in chemistry courses. So there is examples of sharing where it's equal, sharing where it's not, but sharing in terms of electron sharing when it comes to bonding is what we call covalent bonding. It's a very important type of bonding to our world.